Alright, in this video I'm going to be talking about dipoles and the shapes of molecules. So before we can get started, we have to remember that to get a dipole, we have to have an uneven sharing of electrons. So we have to have something like water, H2O, or methane, NH3, where the electronegativity difference between the two atoms involved in the bond is between 0.5 to 1.7. If it's less than 1.5, we call it pure covalent. And we say there isn't an uneven sharing, they're sharing those electrons fairly. And if it's above 1.7, it forms an ionic bond. And the electron difference is so different that the electron is actually transferred. So if we're in this middle region here, 0.5 to 1.7, we say that there is a significant uneven sharing of those electrons, and so we have to look at the shape of the molecule to decide if a dipole will be formed. A molecule could be symmetric, saying that all of the bonds are going in the same direction equally. So for example, looking at our diagrams over here, this one would be symmetric, this one would be symmetric, and this one would be symmetric. That one, and that one. If we imagine the two bonds that are pulling here are pulling side to side and they balance each other out completely. When we say something symmetric, we might think of a tug of war, and if the two things were of equal strength, neither team would be winning because all the people pulling to the left would balance out all the people pulling to the right, and so that's a symmetric molecule. If that's the case, then what happens is, let's say this molecule tries to pull the electrons this way, trying to make this side a little negative, and this same atom tries to pull the molecules all out this way, and trying to make this side negative, but they're fighting against each other. They're both pulling in opposite directions, and so they cancel each other out. And so with symmetric molecules, no dipole is formed. Any chance of the dipole that would have existed due to the uneven sharing gets spread in each direction evenly, say down here, and down here, and then as a result, kind of like forces acting on a single point, cancels each other out and there's nothing left over. Here it's a little trickier to see because we're in 3 dimensions, but all of those pull in opposite directions and down a little, and if you add all of the down components, it would balance out the up component. So those 3 are symmetric shapes. Some example molecules here, this would be like CO2. Oops. This might be like BF3, and this would be like CH4. Now, on the other hand, if the molecule is asymmetric, and this can typically be accomplished by having lone electron pairs on the molecule. So this happens a lot of the time if we have lone electron pairs. Then what happens is the molecule forms into this shape. This particular shape is called the bent shape because it obviously looks bent. So this is asymmetric. And so the electrons might be being pulled this way and this way, but because these things aren't in opposite directions, they don't cancel out. What that means then is that one of these sides can become partially negative and the other side can become partially positive, and in this case, dipoles do form. So our example molecule here would be water. You see the 2 lone electron pairs, and that pushes those 2 hydrogens into that uneven or asymmetric shape. And since oxygen likes electrons more than hydrogen, these electrons get pulled this way slightly. We say the overall dipole, if we tried to think of them added together, goes like that. And we say that this end of the dipole is partially negative, and this end of the dipole is partially positive. Remember, that's our funny symbol, and all it means is partial. Now ammonia, Nh3, is our example molecule here. And what we can see is each of these are canceling each other out on the plane, but they're all pointed down a little bit. So nitrogen likes the electrons more than hydrogen, so it's going to pull them up towards it a tiny little bit. And what that's going to do is make a dipole that goes from the bottom to the top, making the nitrogen partially negative and all of those hydrogens a little bit positive. What that overall dipole, or see, di, which means two, pole, see we have our 2 poles, 1, 2. What that means is that these molecules are going to interact with each other in some different ways that we're going to talk about in some future videos. But in the end, what we're trying to get out of this video is to get a dipole, we have to have a polar covalent bond from 0.5 to 1.7 and an asymmetric shape so that those dipoles don't cancel out due to symmetry. One little exception here that's probably worth mentioning is something like CH3Cl, where this molecule itself has a symmetric shape, but because one of the bonds is different, then the molecule isn't truly symmetric. So this is this shape. So the shape is symmetric, but the atoms are not symmetric. What that means then is that this will have a dipole, because while there are bonds in all directions, one of these bonds is polar, this one, chlorine likes electrons more than carbon, and the other ones are not, so these guys can't cancel out this interaction, and so this guy will become partially negative, and this whole CH thing will become partially positive. And so, to be symmetric, all the atoms must be the same too. On the sides. Right? So if we look at our examples up here, CO2, so these are both O. BF3, these are all F. Or CH4, these are all H. So they can all cancel each other out, versus CH3Cl, where the Cl is different, and so as a result, that dipole does not cancel out.